All right. So before I start, I'd like to acknowledge the large number of the cast of characters that have contributed to this, with whom nothing of this would have been possible, and also acknowledging SSERVI for the funding that was provided. So our project is part of the Toolbox for Research and Exploration, or TREX. That's a SSERVI node that aims to decrease risk to future missions by improving operational efficiency and science yield. We focus on basically spectral characterization of particulate surfaces and the resources that they may provide. Our portion of the research is the robotic field exploration, where we discuss on how we could delegate mission planning, data collection, analysis, and decision making to an automated robotic explorer. So here's the premise. Today's robot exploration is centered on around a very tight circle of scientist, controller, robot, a very tight loop of planning, commanding, and execution going on there, where the controller commands the robot through every single move it makes, every single operation it performs, and awaits for the robot to return to accomplish it before it sends the next set of commands. This process is very slow, as we have seen with the Mars rovers. It will be a little faster on the moon, but it'll still be relatively slow. The other problem is that data rates are usually low. I'm going to take this off. And data volumes are limited. Therefore, the scientists and operators have to work with an incomplete assessment or knowledge of the site, which means that they are making decisions on the basis of limited knowledge, and important observations may be missed. So here we propose a different paradigm, which is science autonomy, where the robot's actions are not constrained by an iterative process of command execution with the operator, but instead they are open-ended and responsive to the observations that the robot is making in the field. This actually delegates a lot of the responsibilities, such as decision-making, data analysis, route decision planning, to the robot. So the aspect of that is that we would end up having an improved operational efficiency and improve the science yield, because the data acquisition and analysis are not limited by communications bandwidth. The rover can acquire a lot more data than it will ever send to the ground. It just needs to send back what it considers important, and what is important is something that can be worked on. So this is how it works. The scientist starts by generating something called a hypothesis map, which is a pool of hypotheses about whatever experiment or exploration that they're trying to accomplish. They give it to the robot, and the robot, with a knowledge of this hypothesis for the terrain, for example, and a knowledge of the terrain itself, topography, solar insolation, and other resources, devises a plan by which it will traverse the terrain, perform observations in order to address the hypothesis that it has been given. You'll acquire, as it travels, it acquires data. The data is interpreted to address the hypothesis, and some hypotheses are weighted towards greater probability, and some are towards less. As that does so, it basically updates the hypothesis map, and eventually, periodically, or when the robot runs into an observation that it cannot explain through any of the hypotheses it has, it contacts the scientist, provides the updated hypothesis map, and whatever relevant data there is. So I would use the hypothesis map a lot. And the best way to explain the hypothesis map, which is really central to this entire investigation, is basically to show you how we create one. So the specific hypothesis maps depend on the objective of the investigation. And here you're free to create your own hypothesis map based on your investigation. In ours, we seek to constrain the geological history of sites visited by the rover. So our hypothesis map is going to look like a cube. The X and Y dimensions are just maps, basically. They're the map of the region. So X, Y pixels are locations. And Z, each plane contains a different geologic origin. The pixel value indicate on each of those, on any one pixel on any one plane, indicates the probability of that hypothesis being correct. So the more minerals supporting that geologic origin, as the rover identifies minerals, the higher the probability value for that pixel. On the flip side, the more planes containing a non-zero value at XY for that at XY, the higher the uncertainty. So now that we have an uncertainty and a probability, we can actually send the rover to explore. The rover's job is to disambiguate geologic origin for each terrain by going to the places of highest uncertainty and performing measurements there. So the generation of the hypothesis map in our case, we started with an average data cube, which is a airborne hyperspectral imager in the near infrared. So here's basically one of our sites. And we basically derived mineralogical maps for every mineral in the USGS spectral library. The maps, the minerals, from mineral constraints, we can basically derive a geologic origin. Some mineral constraints are much stronger on single geologic origins, and some are more ambiguous. So by taking those mineral maps, we basically turned our geologic origin cube, and here are some example planes for lacustrine, photogenic, evaporitic, and igneous, and you can see the gradient of data values indicating the relative probabilities. Now, the next step is actually sending the rover out on the field. At some point, the rover is sitting on an XY position on the map. It performs spectral observations of the area, and it's going to see a lot more, because of the greater spatial resolution, it's going to see a lot more minerals than you could see from airborne data. Therefore, it's going to address basically, it's going to basically rebuild that specific pixel using the minerals it's been detecting. But it's not only that pixel, because that pixel has is spectrally similar or even identical to many other pixels in the. So based on the similarities, when you update one pixel, other pixels which are spectrally similar or geologically in the same geologic unit are also going to be updated to reflect this new hypothesis map. So basically, the rover updates these maps, stops, and then basically decides once again what is its new traverse, because the entire uncertainty map has been recomputed, right? So it basically calculates a new traverse from the point where it's performed observations. So our field campaign basically used the rover Zoe, which has a very innovative suspension and steering mechanism. It's capable of addressing a lot of different hazards, and it has great autonomy. It carries the near-infrared spectrometer, which has the same spectral range as the Avaris. It also carried a pair of stereo imagers and a GRS, and we also carried handheld instruments to complement it. But the only data that was actually used for the specific purpose of addressing the hypothesis map in this case was the near-infrared spectrometer. Future work is going to use more instruments. So there's the rover doing its job. We separated it into two teams. The science team was basically reclused to the operations center, which would be a hotel conference room in Flagstaff or their own homes, and the rest of the team went off to the field to manage the rover and other instruments. So we basically had two operational scenarios. One of them, which was the fly-by-wire, where you tell the robot every single step of everything it's going to make, just like modern paradigm. And then the new paradigm we're proposing, which is the more autonomous rover. So I'm just going to show here the results from the autonomous. So basically, this is one of the two sites we went to. We selected it because it was easily traversable, geologically very easy. For those of you who know geology in the area, basically, this is the Kaibab Formation, which is a shallow marine limestone, dolomite. We have the overlying Moenkopi Formation, which is also shallow marine, and overlying that is a basaltic lava flow. So that's the image, and this is basically the three most significant planes in RGB of the geologic origin map. In this case, lacustrine marine, metamorphic, and igneous, and the colors are basically the combinations of RGB. On the right, you have an entropy map, basically the uncertainty. So the rover really wants to explore the places of greatest uncertainty to be able to reduce that. So what you see here is the rover. Basically, as it's moving around, it's making observations and it's updating the hypothesis map. It really stayed in the areas of higher uncertainty there for a while. And eventually, as it was running out of resources, decided to just beeline it back to the last point. The first and last points were decided on the basis of how far the science team had made it with the rover during the normal operations. Basically, the operations where they're telling the rover step by step what to do, the first scenario. So basically, we gave them similar starting and ending points, and we let them do whatever they wanted to do from there on. So at the end, the result is that the rover basically decided Moenkopi was fluvial, lacustrine. On the Kaibab, also fluvial lacustrine with some combination of metamorphic, which is actually correct. The science team arrived to similar conclusions, which is good. The only difference is that the science team, of course, this was a training run, took about 3 days to complete this traverse, whereas the rover took 3 hours to reach the same conclusions. In the second site, the rover did not reach the same conclusions as the science team, and it was wrong, and that was mostly due to the fact that our geologic origin table had some fault in it associated to the origin of some minerals. But that's where we are right now. We're going to go again in October to another field site to basically using lessons learned to perform this analysis again, and we're going to add more instrumentation to the decision-making ability. So, we're also going to improve our astronaut rover operations, which I haven't talked about, but a third scenario included an astronaut in the loop. We don't talk about it here. So we do need more members for the science team on this. So if you have any interest and have expertise in near-infrared, FTIR, imaging, let us know. We can bring you in. All right. Good.